Grounding and bonding can create confusion sometimes, especially when dealing with residential electrical systems. When installing a 400 amp panel with subpanels, proper grounding is crucial for safety and code compliance. For grounding the 400 amp panel, NEC 250.52 A3 allows for either two 20-foot rebar rods or 20 feet of number 2 stranded copper in the footing. Both methods provide a low resistance path to earth for fault current and lightning strikes. Copper is more resistant to corrosion and may offer a more permanent grounding solution. The choice between rebar and copper often depends on soil conditions and homeowner preference. Now let's discuss the grounding of the 200 amp subpanel. The 200 amp subpanel needs a separate grounding electrode system. According to NEC 250.30 A5, each building or structure served must have a grounding electrode system connected to the grounding electrode conductor at the service. Therefore, you need to install another grounding electrode system for the subpanel consisting of one or more electrodes as specified in NEC 250.52. This ensures that each structure has its own dedicated grounding path. For the grounding system, it is recommended to use rebar rods or copper rods for the electrodes. The grounding rod should be driven into the earth at least 8 feet deep and spaced at least 6 feet apart. The grounding electrode conductors, GEC, should be sized according to NEC table 250.66. For the 200 amp service, you would need to run a separate GEC of number 4 copper from the main panel to the subpanel. This is in addition to the 3 1/0 copper conductors and one number 4 copper GEC for the panel feeder. Remember that the grounding electrode conductor connects the grounding electrode to the panel's grounding bus. It's essential for providing a path for fault current back to the source. The following grounding system would meet code requirements. Firstly, two 20-foot number 2 stranded copper or rebar grounding rods driven into the footing for the main panel. Secondly, one 8-foot number 4 copper or rebar grounding rod driven into the earth near the subpanel. Thirdly, number 4 copper GEC from the main panel to the subpanel, in addition to the panel feeder. Let's delve deeper into the specific NEC sections and requirements. NEC 250 covers grounding and bonding requirements. Section 250.52 addresses grounding electrodes, specifying the types of electrodes that can be used. This includes metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, and ground rings. The concrete encased electrode, often referred to as a U for ground, consists of at least 20 feet of 1/2 inch diameter or larger rebar or at least 20 feet of number 4 bare copper conductor encased in at least 2 inches of concrete. Ground rings are another acceptable option, consisting of a bare copper conductor not smaller than number 2, buried directly in the earth at a depth of not less than 30 inches. NEC 250.30 specifically addresses grounding requirements for separate buildings or structures. This section clarifies that each building or structure supplied by a feeder or branch circuit must have a grounding electrode or grounding electrode system connected to a grounding electrode conductor. This requirement ensures that each building has its own independent grounding path. The size of the grounding electrode conductor is determined by NEC table 250.66, which bases the conductor size on the size of the ungrounded conductors. For example, if you have a 200 amp service, the grounding electrode conductor is typically number 6 copper or number 4 aluminum. It's important to consult the table for specific sizing requirements. In addition to the grounding electrode conductor, the equipment grounding conductor plays a crucial role in the grounding system. The equipment grounding conductor provides a low impedance path for fault current to return to the source, tripping the circuit breaker or fuse and clearing the fault. The equipment grounding conductor can be a wire, a conduit, or other approved metallic pathway. NEC 250.118 outlines the types of equipment grounding conductors that are permitted. Bonding is another essential aspect of the grounding system. Bonding involves connecting all non-current carrying metal parts of the electrical system together to create a low impedance path for fault current. This includes metal conduits, metal enclosures, and metal equipment frames. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. NEC 250.92 covers bonding of metal enclosures and raceways. This section requires that metal enclosures and raceways be bonded together using bonding jumpers or other approved methods. The size of the bonding jumper is determined by NEC Table 250.102, which bases the jumper size on the size of the circuit conductors. When working with subpanels, it's important to understand the difference between grounded conductors, neutral conductors, and equipment grounding conductors. The grounded conductor, or neutral conductor, carries the normal and balanced current back to the source. The equipment grounding conductor provides a path for fault current. These conductors must be kept separate in the subpanel. The neutral conductor should be isolated from the subpanel enclosure, and the equipment grounding conductor should be connected to the enclosure. This separation prevents neutral current from flowing through the grounding system, which can cause nuisance stripping and other problems. When installing grounding electrodes, it's important to consider the soil conditions. Soil resistivity can affect the effectiveness of the grounding electrode. High soil resistivity can increase the impedance of the grounding path, reducing its ability to dissipate fault current. In areas with high soil resistivity, it may be necessary to install multiple grounding electrodes or use ground-enhancing materials to improve the grounding system. Ground-enhancing materials are designed to reduce soil resistivity and improve the contact between the grounding electrode and the earth. These materials can be particularly useful in rocky or sandy soils. It's also important to protect grounding electrodes from physical damage. Grounding electrodes should be installed in locations where they are not likely to be damaged by vehicles, equipment, or other activities. If the grounding electrode is located in an area where it is susceptible to damage, it should be protected by a fence barrier or other means. Regular inspection and maintenance of the grounding system are essential for ensuring its continued effectiveness. Grounding electrodes should be inspected periodically for corrosion, damage, and loose connections. Grounding conductors should be checked for proper sizing and secure connections. Any problems with the grounding system should be corrected promptly. When installing a grounding system, it's important to follow all applicable codes and standards. The NEC provides detailed requirements for grounding and bonding electrical systems. Local codes may also have additional requirements. It's important to consult with a qualified electrician to ensure that the grounding system is installed correctly and meets all applicable requirements. The grounding system is a critical safety feature of any electrical system. A properly installed and maintained grounding system can protect people from electric shock, prevent equipment damage, and reduce the risk of fire. By following the guidelines outlined in the NEC and consulting with a qualified electrician, you can ensure that your electrical system is properly grounded and protected. Remember to always prioritize safety when working with electricity. Turn off the power before working on any electrical equipment and use appropriate personal protective equipment. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Grounding is not the same as bonding. Grounding connects the electrical system to the earth. Bonding connects non-current carrying metal parts together to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. When installing a subpanel, it's important to follow the manufacturer's instructions carefully. The manufacturer's instructions will provide specific guidance on how to properly ground and bond the subpanel. It's also important to use the correct size conductors and connectors. Using undersized conductors or connectors can create a fire hazard. When running grounding conductors, it's important to avoid sharp bends and kinks. Sharp bends and kinks can increase the impedance of the grounding path, reducing its effectiveness. Grounding conductors should be run as straight as possible. When connecting grounding conductors to grounding electrodes, it's important to use approved connectors. Approved connectors are designed to provide a secure and reliable connection. Avoid using wire nuts or other makeshift connectors. When installing grounding rods, it's important to drive them into the earth to the proper depth. Grounding rods should be driven at least 8 feet deep. If the grounding rod cannot be driven to the full depth due to rock or other obstructions, it should be buried horizontally. When burying a grounding rod horizontally, it should be buried at least 30 inches deep. When connecting multiple grounding electrodes together, it's important to use a continuous grounding conductor. The grounding conductor should be sized according to NEC Table 250.66. Avoid splicing the grounding conductor between grounding electrodes. When installing a grounding system in a corrosive environment, it's important to use corrosion-resistant materials. Copper grounding electrodes are more resistant to corrosion than steel grounding electrodes. Galvanized steel grounding electrodes are also available. When installing a grounding system in a hazardous location, it's important to follow all applicable requirements. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Grounding systems in hazardous locations must be designed to prevent sparks and other ignition sources. When installing a grounding system in a healthcare facility, it's important to follow all applicable requirements. Healthcare facilities have special grounding requirements to protect patients and staff from electric shock. When installing a grounding system in an industrial facility, it's important to follow all applicable requirements. Industrial facilities often have complex electrical systems with high fault current levels. Grounding systems in industrial facilities must be designed to withstand these high fault currents. When installing a grounding system in a commercial building, it's important to follow all applicable requirements. Commercial buildings often have a variety of electrical equipment, including lighting, HVAC systems, and computers. Grounding systems in commercial buildings must be designed to protect this equipment from damage. When installing a grounding system in a residential building, it's important to follow all applicable requirements. Residential buildings have simpler electrical systems than commercial or industrial buildings, but grounding is still essential for safety. Remember, proper grounding is a critical safety feature of any electrical system. By following the guidelines outlined in the NEC and consulting with a qualified electrician, you can ensure that your electrical system is properly grounded and protected. Always prioritize safety when working with electricity.